Hi, me again, Mr. Weiser, here to go over chapter 5 in this textbook here. This is going to be on this midterm review packet that is linked to this video description. And if you're in my class, you should have a copy of it. Let's begin. We're going to be talking about probability rules. This is part of a larger unit that covers probability and random variables, which is chapter 5 and chapter 6 in this textbook. The first thing you want to talk about for probability rules is just the general formulas for the or and the conditional probabilities. When you take your AP exam, on your formula sheet, you are given these two formulas here. So they look like they're in kind of a formula sheet mode because, well, that's on the formula sheet. This represents given. And when you're doing a given, a conditional probability, this means the overlap. This is the overlap. This is the and, okay? This represents or, that's their combined. When you're doing an or, you add the two individual probabilities and subtract the and, the overlap. So we add them, we subtract the and. There's some other rules about independent events and the plus, the at least ones and et cetera. I'm going to leave you just looking through that because I'm not going to explain every single detail that's printed out here. But let's begin on going over a few questions. So there's going to be a few questions on here. If you would be patient, let's go through them all. Try every question first before you watch the rest of me work it out. So I would want you to pause the video and think, try the problem. Here's the first question. 47% of her shots from the field. We want to simulate a player taking sets of 10 shots, assuming that her claim is true. I believe there's some missing information on here, but this question is talking about a person that makes 47% of the shots on their field. We are trying to simulate this 47. So we're taking 10 shots. Let's think about how that looks. If we're simulating a 47% chance of taking shots on the field, there's a couple of different ways we can do it. If you're using two-digit numbers, which is what I would recommend here, you have to think about, are we going from 0, 0 to 46 or 0, 0 to 47? And a lot of people are gonna select 47 without thinking that this represents a number 2. So 0, 0 is kind of like your first number. So that's actually 48 numbers, and we don't want that, okay? So what we want to do is we want to represent 47%. So it would be either 0, 0 to 46 here or 0, 0 to 46 here, because this is 1, and this would be the 47th, so this is 47%. So it's down to those two. The other ones are a miss, so we have to go over here and we have to determine what's going to simulate this shot. And the question says we want to simulate the player taking sets of 10 shots. So each simulation is 10 random draws. Each draw is a shot. And when you do 10 random draws, you're going to get a number between 0, 0, and 99. If you are between 0, 0, and 46, it's a make. If you're between 47 and 99, it's a miss. But you're only doing 10 shots, so you're only doing 10 random two-digit numbers. So it's going to be B. It would look something like this. So what this simulation would look like is you would have a bunch of different rounds of these choosing 10, and you're either going to hit all 10, which is very unlikely. It should probably, if the simulation is done correctly, should be centered somewhere between like 40% and 50% because we're trying to simulate that 47%. So that's kind of where we're going with that. That's what a simulation looks like. But again, it's going to be answer choice B because we want to simulate, and I got my numbers all kind of misaligned here, but we want to simulate. There we go. The 47% here. So you want to pick 0, 0 to 46 because 0, 0 counts as 1. All right, let's go on to the next question. All right, question number 12. In government data, a household consists of all occupants of a dwelling unit. Choose an American household at random and count the number of people it contains. Here's the assignment of probabilities of the outcome. The probability of finding 3 people in a household is the same as the probability of finding 4 people. Find the probability that a chosen household contains more than 3 people. First thing you have to know is in probability distributions, these are all going to add to 1. And the only way you're able to get 3 and 4 in this case is that we know what they add to, but in this case, the probability of finding 3 people is the same as the probability of finding 4 people. So we can figure out what 3 and 4 are because we can add these numbers together and subtract from 1 and divide by 2. So what I would do on a problem like this is I would just kind of call these both x. And then I would set up an equation. Since I know probability of 3, probability of 4 equals the same, I would just say something like this. I would say 0.25 plus 0.32 plus 2x, 0.07, 0.03, 0.01, and just make sure you set that equal to 1. Now, you take a moment to solve that out and see what you get for x. These numbers should add to 0.68. And so you can subtract that from 1 to get 0.32 and divide. So x should be about 0.16. So if I go over here, 0.16, 0.16, and you can verify, do these all add to 1? And of course, the answer is yes. So we are good to go on that round. Now, as far as answering the question says, find the probability that the chosen household contains more than 3 people. So if I want to show more than 3 people, then I have to look at more than 3, which is 4, 5, 6, or 7 and higher. So those are the more than 3. Or is just adding them together, but it's basically what's the probability of 4 or 5 or 6 or 7. So you're going to get about 27%. 0.27 or 27%. All right, on to the next question. Question 13 is a multi-part question. We'll do it in different parts here. So let's look at that first one. Researchers carried out a survey of 4th, 5th, and 6th grade students in Michigan. Students were asked whether good grades, athletic ability, or being popular was most important to them. The two-way table summarizes the survey data. I want you to realize that a lot of times on these two-way tables, they're going to give you the totals, but every once in a while, sometimes they hide them, okay? So it is your responsibility to look for totals. If you don't see them, my first go-to would be to redraw this out and add them along the columns and the rows so you can get your totals, including getting your overall total so we can get that. Fortunately for us, we have those numbers already. So let's answer the question. What is the probability that a randomly chosen student from this survey was in 5th grade or chose being athletic as most important to them? So when you talk about 5th grade or athletic, we're talking about all the 5th graders and all the athletic. But if you only do those two numbers, you're not taking into account that there's a number that is part of both of those. And we have to subtract that. So when you're doing your probability rule, remember your probability rule looks like this. Probability of A or B is equal to the probability A plus the probability of B minus the probability of A and B. So what am I looking for in this is something like this. In terms of events, I would say probability of 5th or athletic is the probability of 5th plus the probability of athletic. So that's the 108 out of 335 plus 98 out of 335. But then I want to subtract the overlap, which is 36. So it's going to look like this. 108 over 335 plus 98 over 335 minus 36 over 335. And when you calculate that out, you can leave that as a fraction or a decimal. It doesn't really matter. But you get 170 over 335 for your final answer. Now let's look at the next part. All right, guys, the next part is, given that a randomly selected student from this survey was in 5th grade, what is the probability that they chose being athletic as the most important to them? I'm going to erase this. And this is going to deal with your conditional probability formula, which looks like this. Probability of A given B is equal to the probability of A and B, that's the overlap, over the probability of the given. So I want to think about this. What are we given? Given that a randomly selected student was in 5th grade. So out of the 5th graders, this is what I'm given. Only those numbers, not all the 335, just those. That's my denominator. The question says, what's the probability that it chose being athletic as the most important to them? So I want to go back and I find in this column, athletic of those, just those fifth graders, is 36. So that fraction is simply going to be 36 over 108. So you'd set it up like this. Probability athletic given fifth, and remember it has this little line here to represent given. We do the probability of both, which is 36, over the probability of just the fifth grade, which is the 108. All right, there's another part. Okay, part C. Among the students in the survey are being fifth grade and choosing being athletic as most important to them, independent of each other. Wow, let me read that again. Among the students in the survey are being in fifth grade and choosing being athletic as most important to them, independent of each other. And what you're looking for in independent, let me bring the numbers down here, is what it means without any numbers is, does knowing somebody being in fifth grade impact whether or not they choose being athletic as the most important to them? If it does, you'll see the probabilities differ between athletic versus athletic given fifth grade. So there's a couple different ways you can use the table on here. I'll start with this one. We're going to do a conditional probability. So let me cover that up for a minute. We want to compare these two probabilities. In other words, is the probability of being athletic given fifth grade? So we just did this, 36 out of 108. Is that any different than the probability of just being athletic? So we kind of look in the table, we go over here and there, and we want to see, are they the same or are they different? Which one is it? So we test those. We use our calculator, of course, and we do 36 out of 108 and 98 out of 335. And you want to compare the decimals because these fractions are, of course, pretty large to kind of try to figure out which one's bigger or less or the same. So we divide them out and we get these two numbers. And notice that they're different. Knowing that somebody's in fifth grade, the probability that they're going to pick athletic increases that probability just a little bit. So since these are not the same, that tells you that they are not independent. They are not independent. If they were independent, they'd be the exact same number because those probabilities didn't change. You could also do it going in the other direction of the table. So what you could say instead is, you could say, is the probability of being in fifth, let me use a different color for this, is the probability of being in fifth grade given their athletics. So if I look at over here, is 36 out of 98, so 36, fifth grade given athletic, the same as being in fifth grade. So in either case, you're going in the same direction. And you could do that here. You could say is 36 out of 98 equal 108 out of 335, in which case they are different. They're different numbers than over here, but it doesn't matter which way you do it. Notice that they're not the same. So since they're not the same, they're not going to be independent of each other. Now, what do you write up as a as kind of a statement? You say something to this effect. Since these two probabilities are not equal, these events are not independent of each other. In other words, knowing that a student is in fifth grade changes the probability that they chose being athletic. Now, you don't have to do both of these. You can do one or the other. So that's why I said or. You have to show some numerical evidence from your table and back it up with those numbers. All right, on to the next question. Question 14. Suppose that you have a torn a tendon and are facing surgery to repair it. The orthopedic surgeon explains the risks to you. Infection occurs in 4% of such operations. The repair fails in 10%. And both infection and failure occur together 2% of the time. What is the probability that the operation is successful for someone who has an operation that is free from infection? So before I do all the work in here, I want to know what the question is. So the question says, what's the probability that the operation is successful? So I'm going to just write a statement. Probability of success for someone who has an operation that is free from infection. So given no infection. At the end of the day, this is a conditional. So that's what we have to work with, okay? Now, in a problem like this, when there's no table, there's no diagram, it's best that you make one. In this case, screams Venn diagram. So let's set up what we can, okay? We have two main type of things. We have infection occurs in 4% of such operations and fails in 10%. So I'm going to start with infection and fails. Now, what we know is that in this problem here, it does say both infection and failure occur 2% of the time together. So I know that I can put my 2% right in there. Now, as far as the other ones goes, you got to remember that when it says infection occurs 4% of such operations, that represents the whole circle. So 4% is all of that, not just the part that's not the 2%. So we have to figure out, well, what is the part that's just outside of that Venn diagram overlap? And what you can do is you can take that 4% and subtract the overlap, and you're going to get 2%. So this number right in here is actually going to be 0.02, because those added together will give you the overall 4%, which if you want, you can write that 4% right here so you can recognize it's those two added together. Same with the failures. The failures, repair failures are going to be 10%. But what I want to think about is, well, if I know 2% is the overlap, then I want to subtract that and get 8%. So you're going to get 8% over here in this portion. And those two together, of course, are going to add to 10%. So those two add to 10%. These two add to 4%. And of course, there's an overlap there. Well, that leaves you with some stuff left over. And if you look at these, if you add these three numbers, you're going to get 0.02 plus 0.02 plus 0.08. Well, there's got to be some leftover, because that's only 10, that's 12, that's going to be 12%. So there's going to be 88% that fall into neither of these categories. So that math is just going to be 1 minus 0.02 minus 0.02 minus 0.08 to get you that 88%. So there's your Venn diagram. Now we can answer the question, okay? So we've gone through and we've gotten everything but is in terms of what the question's actually asking. So let me go down here and let's think about what the question wants. The question wants to know what's the probability that the infection occurs, or what's probably the operation is successful for someone who has an operation that is free from infection. So this is the conditional statement. That's what I wrote up here originally. Successful given no infection. Now we have to set it up with numbers, okay? No, successful means no fail. Successful is not failing. So where is it going to be successful? It's going to be successful anywhere that's not in this circle, okay? It's going to be anywhere that's not in here. Now, no infection. No infection is going to be anywhere that's outside of the circle, including out here. So I want you to think about what that looks like. It's going to be a conditional probability. It's always going to be the and on top. So the probability of no infection and no fail. Well, where is no infection and no fail occurring? No infection is out here. No fail is out here. They only overlap where they're not in the circle at all. So no infection and no fail is going to be 0.88. That's going to be your numerator. Now, because this is a conditional, we have to say, given no infection, we have to find out what is the percent of no infection. So let's think about what the percent of infection is. We're given that. The percent of infection is 4%. So everything else is no infection. 1 minus 0.04 is no infection. Well, what's that going to be? That's going to be 0.96. So this probability wants you to calculate 0.88, 88%, divided by 0.96. So he wants to add that 0.08 and the 88% on the denominator. And that'll give you 0.96. Divide those out and get a decimal. And you get 0.917. 0.917. So the probability that the operation is successful for someone who has an operation that is free from infection is about 91.7%. All right, one more question in this video. Question number 15. According to a recent poll, about 42% of US adults have tattoos. If you were to randomly sample 5 US adults, what is the probability that at least one of them will have tattoos? The way at least ones work is you have to think about the probability of none of them having tattoos. And if I did a sample of 5 in this case, what's the probability that none of them have tattoos? The probability of at least one of them having tattoos is going to be 1 minus that. So you set it up like this. You find the probability of tattoo, you find the probability of no tattoo, and that's just one person. So now you want to select 5. What you want to do is you want to say, if I sampled 5, what's the likelihood that none of them are going to have a tattoo? And so you're going to say probability at least 1 is 1 minus the probability of none. And so let's calculate that. The probability that none have the 5 tattoos is going to be 0.58 times 0.58. We always use multiplication when we're dealing with independent events. Another easy way to do that is to do 0.58 to the 5th power. So in your calculator, you'll type in 0.58 to the 5th power, and you get about 0.0656. Now, from there, you're going to take that number, 0.0656, and you subtract that away from 1, and that'll be the probability at least one of them will have a tattoo. So you do 1 minus that, and you'll get about 0.9344. You can also use a binomial. Let me pull up my calculator so you can see how I input that. If you want to use a binomial, which is actually part of Chapter 6, but since you likely have learned Chapter 6, you can get away with doing it this way too. For a binomial, what you'll do is you'll do second vars, binom, and you can actually do CDF or PDF. It doesn't really matter because you're going to put 0 in anyway, and everything adds from there all the way down to 0. You're selecting 5 people. You want to know the probability, so 42% for 1, that none of them, or that at least one get a tattoo. So you can do 0, and you can click paste, and you get about 6.56%, and then you can subtract that from 1, and there's your 93.436. You could also do, although it would take a lot longer, you could do binomial, PDF, and you could do it with 1, and then you could do the same thing and do 2, 3, 4, and 5, and you could add them all together to get that 93%, but that would be pretty time consuming. So I'd recommend using the complement and just subtracting from 1 to get your answer. Thank you for watching this. The next video is going to be still in the same unit. It's going to be unit 4, but it's going to be chapter 6, random variables and binomial and geometric probabilities and all that stuff. So thanks for watching, guys. Stay tuned for the next one.